Welcome to this video. In here we're going to talk about Venn diagrams. A new detergent is found to remove excess dirt and stains satisfactorily on 88% of the items washed. Assume that 3 items are to be washed with the new detergent. A. What is the probability of satisfactory results on all 3 items? B. What is the probability that exactly 2 items are cleaned satisfactorily? C. This should be a C. What is the probability that none are cleaned satisfactorily? So basically, we're just reviewing the concepts we learned from last video to apply here. The probability of satisfactory results on all 3 items will be 88% times itself 3 times. So 88% cubed, which is 0.681. The probability that exactly 2 items are cleaned satisfactorily. So we want exactly 2 items. Therefore, we use 0.88%. That is the probability of cleaned satisfactorily times the last atom that has been not cleaned satisfactorily, which is 1 minus 0.88. We get 0.12. We times these 3 values and get 0.279. Part C, the probability that none are cleaned satisfactorily. We would use 1 minus 0.88, that quantity raised to the 3 power. Therefore, we get 0.0017. Okay, so that's just a little recap exercise. And finally, let's see how a Venn diagram can be a very useful tool for solving problems with conditional probabilities. At Comic-Con 2023, all attendees to a breakout session on the Undead are given a card to fill out. So this is a little scenario. Do you like vampires? Do you like water, like werewolves? Not really sure what that is. But you can just like circle or like check mark yes or no for each. And all 400 attendees filled out the cards and turned them in. Of the 400 attendees, 132 checked the box that they like vampires, 281 checked the box that they like werewolves. Upon closer inspection, it was also noted that 75 checked both boxes. And what we want to do is we want to find out, like using the Venn diagram to find different probabilities. So if we want to draw a Venn diagram for this, there are total 400 attendees, and 130 to check the box that they like and vampires. So 57 plus 75 will be 132. They checked both, like 75 will go in the middle. So what you can find out like the region on the left and right, you're just going to use 132 minus 75, get 57 right here, and use 281 minus 75, get 206 right here. And there's left 62 peoples. So 62 should go out of the circle, but still in the box. The box is represent 400 attendees. That's the whole population. So let's take a look at some conditions. So So I am gonna use V shorthand for vampire and WW for werewolves. Probability of vampires or werewolves is going to be 338 divided by 400. That's 57 plus 75 plus 206. That's how I get, that's how I get that number. And you can also use probability of vampire plus probability of werewolves minus probability of both. That's the formula we learned last video. And getting the probability separately and adding and subtracting, get the final result too. The probability of werewolves, getting werewolves given that people checked vampires. So basically, you can also use the formula that we learned last video, which is using the probability of both divided by probability of vampire, which gives you 75 divided by 132. And let's ask ourselves a question. Are vampire and werewolves independent to each other? We're going to check if they're independent, then probability of getting vampire should be equal to probability of getting vampire given werewolves. And after doing all the calculations, we get, no, they're not independent, so which means that they're dependent. Or you can also use probability of werewolves. Is it equal to probability of werewolves given the vampires? You can see that you get the same result. The numbers may not be the same, but the conclusion should be the same. They are not equal to each other, therefore they're dependent to each other. Okay, so moving on to this little diagram right here. A lot of colleges, universities yeah, if you want to pause for a sec to see if you're a college or high school student, I assume most of you are high school students who are watching this video, but maybe your dream school are here. I saw a lot of my dream schools. Okay, whatever. Take a look at this question. According to the American Pet Products Manufacturers Association, also known as APPMA, sorry for that. Trying to adjust the size of the screen. It's always hard for me to do it. Okay, 2015 to 2016 National Pet Owners Survey, 39% of U.S. households own at least one dog and 34% of U.S. households own at least one cat. Assume that 60% of U.S. households own a cat or a dog. Part A, what is the probability that a randomly selected U.S. household owns neither a cat nor a dog? So we want to see the household in U.S. own either. Therefore, we can first create a Venn diagram. It will be a lot more easier for us to do these type of questions. So there are 13 there are 60% of households own a cat. Okay, so which means that 0.4 or 40% of the US household own neither. 0.4 should go in here. This whole area should add up to 0.6. And 39%, so we want to know that 0.26 plus 0.13, it add up to 0.39, and 0.13 plus 0.21 also add up to 0.34. Okay, so yeah, so this is how you create a Venn diagram for this. We want to know that a random owns neither a cat nor a dog. So basically right here, we don't know the middle area, the probability of the middle region. So we just assume we don't know, even though I already wrote it down here. But the probability that owns neither is going to be 0.4. You use 1 minus 0.6. Part B, what is the probability that a randomly selected US household owns both a cat and a dog? Both a cat and dog, it is 0.13. So how are you going to do that? Well, you're going to use the formula we learned last video. Can set up the equation like right here. The probability, sorry, it's hard to see, but basically you're going to use the formula we learned last video and get 0.13. Part C, what is the probability that a randomly selected US household owns a cat if the household has a dog? So you're going to use probability of cat given a dog. So 0.13 divided by 0.39, you will get 1 over 3. So that's the answer for part C. And part D, I add one more question. Are cat and dog independent to each other? You're going to use probability of cat, setting that equal to probability of cat given dog. We're not actually setting it because that's the reason I add a question mark right here. We're just checking if these two equations equal to each other, and they're not. So they're dependent to each other. Same thing, you can use probability of dog, checking if probability of dog given cat is equal to probability of dog. No, it is not, so dependent. Okay, so that's all for this video, and I hope you learned something from it. Thank you so much. And also, like, this cute little diagram right here, it shows like different conditions for each university, so kind of surprising me a little bit. If you want to dig deeper into it, you can. But anyway, that's all for this video.